Hello again. It's a long time since my last update. A lot of miscellaneous projects going on and some troubleshooting here or there if you've seen any of my little GitHub posts or videos in between. But I figure I'm long overdue to update on some of these projects, and I figured I can actually throw in some voice audio this time. So forgive me if my voice is a little grating or irritating. I'm not usually not used to adding in voice clips. So updates on the clip map system. I rewrote the whole thing essentially. I was able to reuse a few parts, but I just didn't get the flexibility, and the transitions between the levels of detail weren't looking as good as I would have liked them to with the pre-baked Blender meshes. So I rewrote it to utilize at runtime generated meshes. So each of the components is now generated in script, in GD script, and created at runtime. Surprisingly fast and efficient. Only takes a few milliseconds to regenerate several different LOD layers, so that's a lot more efficient than I thought it would be. And of course, gives me more granular control of everything. So I'm able to apply vertex coloring and some other things I can do with the mesh data now. All right, so this might look a little familiar. I've just got a noise texture turned on right now. I've got a little player object, and in case you haven't seen the previous videos, essentially the clip map system works like this. It gives us this infinite level of detail for terrains that if we look at the wireframe, you can kind of see what's going on here. Although the flat shading should also help it make it look more obvious. And you can see as we get further and further out, we get lower and lower and lower resolution by binary increments. What this does mean, though, is that for every transition is going to require 2 movement increments to add up to a single update. So the most high resolution internal level of detail will move twice before the next one will move once. And these little individual pieces that are now a little better color coded with the vertex shaders allows you to see these individual filler pieces moving around. So this is essentially what's happening on the back end. All of these mesh pieces are moving around to track the player, and you can see they update in pretty much any direction. And what we're doing is we're locking the vertices and the meshes in place so that as things move around, you don't really actually see any vertex movement. So you'll see even as this player moves around left and right, we don't actually ever see these triangles change, which is good. That's what we want. Otherwise you get this kind of shimmering, swimming effect across the screen, which is not great to look at. So right now I've got a flat shading effect enabled, and I have the coloring turned on the mesh components. And you can see here, this is a different technique from what I was using before, but this is called skirting, where essentially we're dropping some extra face geometry in between the transitions to cover up the holes, and then doing some shader magic to give it the same normals, so that when the when light hits it, it doesn't actually interact with it in a way that'll make it visible. So you shouldn't actually see it. So right now you'll see it because of the colors that are enabled on it, but that's it. So if I actually turn off the visualizer and the flat shading, it should disappear. Yep, they're gone. So I can turn on the visualizer again so you can see that bright magenta color, and toggle it off and they disappear. So kind of a cool little ability to do that. So another big update is I was able to finally get proper working normal calculations from height map. So you can see right now we're only using a height map, no normal map, no diffuse map either, but that's okay. So, and we have relatively proper working normals right now. The specularity is really high because the roughness is set down really low, but the normals are working correctly, which is what we'd like to see, calculated from the height map sampling. So one of the things that I was able to do with this is right now we're calculating the normals per vertex, So as the mesh resolution changes, it actually becomes very apparent. You can see the transitions because there's less vertices. It means there's less calculations, and it kind of leads to this ugly effect as it moves out and out. You get lower detail, and it becomes very apparent. So what we do is we use interpolation to pass the vertex shader information to the fragment shader and perform our calculations per fragment, or more akin to per pixel rather than per vertex. And so I've got a blending value set up for that, so I can scale up the actual fragment interpolation. And so now you can actually see the difference, especially in the distance. It doesn't make an enormous difference up close at the highest level of detail, but the further away, especially you get from the camera, the more you see that it actually looks almost exactly the same across everything, which is fantastic because the level of detail is still dropping. So pretty cool little feature there. Got that working, and this is of course still without using any actual normal maps. This is all generated from the height map. So pretty nice to have that capability because if you're doing any procedural generation, obviously you won't have pre-baked normal maps. So getting that working is a pretty big victory. All right, let's see, next thing on here. So the next thing I want to talk about is collision generation. So one thing you run into when you are doing dynamic terrain generation or shader vertex manipulation this way, such that we're changing these vertex values at runtime. Aside from having to recalculate the normals, which we're able to solve, the other issue is that the CPU is never made aware of these actual vertex positions. So this information all sits in the graphics card. It's all very efficient, runs very quickly. However, as far as gameplay logic and physics is concerned, none of this actually exists, right? It's pretty to look at, but we can't actually interact with it. So we have to generate a collider for this. Normally, you can generate colliders on object import, or you can manually create some collider shapes. If we're creating this terrain at runtime, that's not the luxury we have. So what we need to do is we need to generate colliders by sampling these textures at runtime. So one feature I've already implemented here. So before I get into the actual collision mesh creation and generation, one other thing I want to demonstrate is that I've implemented dynamic resolution capability with adding in the mesh generation in the code as opposed to using the pre-baked meshes from Blender. So this gives me a lot more flexibility there. So we're able to regenerate the terrain layers with much more control, and we can scale it up and down that way too, so we can get a much higher detail, lower LOD if we need it. Right now it's around 1 square meter, and it's actually relatively simple if we need to, for example, use a more realistic scale here. So let's go with maybe a 60 meters, and we reinitialize. So the whole thing is regenerated now with a much higher resolution and 8 layers. 8's actually significantly more than we probably need. In fact, we can probably go ahead and scale this back down to maybe 6 layers. And it's still out past the view frustrum, so it's at least 5,000 meters out. You can kind of see the edge right there. But anyway, we've got it regenerated with a much larger initial LOD layer, so it puts that initial transition further away from the player, which is what we want, and we can scale down the terrain. So if we scale down the actual terrain itself by, say, half, and then we need to move the player, though, to get it to update correctly. So now we have about a half meter square resolution at the lowest LOD layer. Now, of course, this does mean you'll need more LOD layers to cover the same amount of distance because we scaled the whole thing down, but we do get a higher level of detail at the lowest one, and otherwise still functions relatively the same. So nice functionality built in there, and of course everything is supported. There's a bunch of extra math that has to go into that, but including the sampling. Never mind the manically laughing toddler in the background if you can hear that. So now that we covered the resolution scaling and we've scaled back up to more normal values, around 60 square meters. We'll talk a little bit more about the actual collision generation. You may have actually noticed a little visualizer kick in occasionally as I move the player around. That's a debug feature. Right now I currently have a kind of a low sample value, so over a 32 square meter area we're only getting 8 square samples. That's 8 on the X and Z axes, or Z, however you like to pronounce it. So realistically we'd want that to be a little more high resolution. But you can see as the player moves around, the process of creating the collider entails actually performing the same calculations that we would inside the shader to get the visual displacement of the vertices on the CPU in GDScript. Obviously, this is not nearly as fast or as efficient as the GPU can calculate it, so there are some limitations that are involved in terms of how much of an area we can calculate at any given time at runtime. So for the time being, we're going to simply generate small samples at any given time to allow this to perform at runtime. And we're going to want it to more accurately reflect what we currently are seeing on the mesh. So we really want this to be more of a 1-to-1 value instead of a 4-to-1 value. And as you can see, they're lining up pretty nicely. Another thing that's kind of gee-whiz trivia is that we actually have to incorporate a half pixel value inside the shader because the shader API with GLSL actually samples textures at the edge of a pixel. Whereas in GDScript, if you're sampling a pixel, it samples from the center of the pixel. So the only way to get those values really pixel perfect and lining up just right with each other is to make sure that we add in that half pixel value for the difference. And as you can see, these are doing pretty nicely in terms of ending up in the right places. So we're going to go ahead and change that sample value here. So let's just go with a 32 by 32. This is no longer going to work quite in runtime because of the debuggers more than anything. So the little visualizers are going to cause a bit of a hiccup because it has to generate so many of them. But as you can see, we're pretty nicely covering the terrain and actually kind of a very visually pleasing aesthetic. And you could probably reuse the same code as part of the splat map entity generation. So when we go to add things like trees and grass and things of that nature, we will be able to reuse the same sampling code to find the surface of the terrain. Or that, or just use the colliders, either or. But if it's a far enough distance away, this is probably the safer way to do it. Okay, so we're going to go ahead and just quickly edit the script to turn the debugger off. So now we should see it's much, much faster. In fact, we're performing all of our samples in runtime now at this point, even with 32 by 32. And we can in fact take that up to a 64 meter area with a 64 resolution, which will give us that 1 square meter resolution for our colliders. And we'll see that it's actually still running pretty much at runtime, or real time. We're getting samples in 2 milliseconds. So obviously this isn't something we want to be doing all the time, between 1 and 2 milliseconds. However, that's how it's set up for now. Ideally, what I want to incorporate, and I have not finished the system for yet, is collision chunking. So essentially we'll bake out maybe 9 surrounding chunks or mesh areas and create those colliders to have them already exist. And then as the player moves, we'll buffer out and stream the generation of the other areas as the player moves around the map to have those ready to go. Now, obviously, there's some weird limitations on this, right? When we're talking about colliders, there's a lot of things that entail. So anytime we need anything, not just the player to interact with the world or the terrain, we're going to need a collision layer available. So even for simple raycasting, if we want to draw a raycast from the camera and detect that we've actually hit terrain somewhere, it needs a collider. So if we were to be firing projectiles or anything of that nature that needs to actually impact this terrain, a collider has to exist at that location. So there's a few different techniques that I'm going to try and incorporate to handle some of these things. I'll probably make a separate video on that because there's a lot of different options and techniques in terms of how we either cover the entire map or generate only the ones that are needed at runtime, or even dynamically change the resolution of those colliders, which we have the capability for built in right now. but like I said, I'll have to address that in a different video. So another really neat GWiz piece in here I want to demonstrate is I've also got this fun little thing built in on the shaders for the terrain that we can now wrap this fake artificial horizon effect. So one kind of cool effect that this has, you kind of have to zoom out to actually see the feature. So we get this fake curvature built into the world, which helps us push the appearance of a spherical planet or anything of that nature without actually needing to make a spherical planet. And you'll see that as the player actually moves around, we deform the world to create and maintain that effect. There's some limitations built into this, but for really basic use cases, this is enough to just provide the visual aesthetic without requiring a complete rewrite of the physics code to allow gravity and things like that to perform normally. So just a kind of a fun thing. And also some GWiz is the whole thing is also invertible, so you can change quite a few values for this horizon effect. So we can make it very steep if we want. We can change the fall off values here as well. So we can change this to a very low safe area. This is the area that is rendered flat. So basically anywhere we're having priority colliders perform, we want to be relatively flat. Since obviously this is just a visual effect, it's not going to affect physics, it's not going to affect the colliders. We want to be really careful about that. So this whole area is rendered flat effectively. And of course that max end value is where we interpolate out to. So we can flip this value upside down as well. Not that I can think of any really good use cases for it, but it's kind of a neat effect that you have this world inverted as well, kind of like you're inside of a planet, or inside out, right? So it kind of gives you this almost motion sickness inducing effect of feeling like you're always falling in the wrong direction. So kind of fun effect to play with, but nothing that I'm too interested in using right now. Just wanted to make sure the capability was there. So since we talked about the colliders, we can actually go ahead and demo the use of the colliders and talk a little bit more about a kind of an update on the physics engine side of things. So in Godot 4.0, they have removed the bullet physics engine and limited it to only the in-house Godot physics. This is better for most use cases. However, on larger and more complex colliders, such as any convex shapes, terrain shapes, or height map generated shapes, there are a number of issues with incorrect normals being detected. If you've been on GitHub, you might have seen my tickets troubleshooting this matter, and it's actually been one of the major delays in terms of my updates, is trying to troubleshoot that whole ordeal. But that said, I've had to work out, in the meantime, a alternative. So I have built a new physics-based player controller. It's no longer using a kinematic or character object anymore. This is based on a rigid body and a bunch of custom stuff that is generated at runtime. So we'll actually go ahead and just demo the project here, test the colliders out. So you can see we got this little cubey dude with legs. He's got some procedural legs in here. Everything's just placeholders right now. Obviously, I'm just using this instead of the capsule for the time being. So he is using 2 raycasts that are dynamic in terms of how they predict. They're predictive in terms of where they sample the terrain on movement. Since he's very wobbly right now because I haven't gone in and fine-tuned any of his values. But since it is a rigid body, he is also subject to any outside physics forces. So we can actually push him around and have him interact with physics much better than you could with a normal kinematic object. Obviously, this means it's a little more complex to write the code to control it, since we don't directly set velocity or position typically on the player. That is the one benefit to using a character body or kinematic object. However, if you can do the math on it and incorporate your mass with your forces, then you can still manage to work out the same kind of effects and make the same sort of movement systems. So obviously we've got more debuggers and things turned on here, and the procedural walking that is very far from being complete of any kind. Obviously it's just placeholders for now, and the legs don't even properly alternate. However, it is a good demonstration of the fact that we have managed to sidestep the collision detection issues with the terrain and reincorporated a number of the physics principles that we kind of depend on, such as being able to properly change movement speed going up and down hills, having proper jump physics, and in fact having a little more cartoony physics for that matter. As you can see, the player has a little bit of spring and bounce to him when he goes to recover, and for that matter, can basically even enable tumbling and rolling, or almost a ragdolling effect, which is kind of a neat side effect of doing it this way. And we also have this kind of built-in lean, which again is a little exaggerated right now. I need to retune it. I haven't set the values very well for this, but just kind of a fun overall player controller. Since I had to do it anyway, to get around the collision issue with the terrain. So figured I'd show that off, and of course these little debuggers. So on top of the visual debuggers, I added in some physics debuggers, and these have very large masses that I can spawn. Obviously, still some more issues here too with Godot physics. Um, Basically, you have to have continuous collision turned on for any rigid body, so or else they will just pass right through the majority of the terrain. So not great, not the best thing in the world, but we'll address that as it gets fixed. So that's a little demo of this, and I think that covers pretty much everything I really wanted to go over with the physics-based player controller. On the bright side, we do have at least one person on the Godot team currently trying to troubleshoot the physics collision issues. You can see that on GitHub. So I'm hopeful, and I know that Juan or Reduz, however you pronounce it, has at least commented that they are aware that it is one of the major limitations of Godot 4 right now, and so that hopefully it's pretty high on their priority list, as it kind of limits anybody who can't create their own physics controllers to do anything like this in large open world environments and things of that nature. So that's a little bit of a bummer, but I'm hoping to see some progress on that, maybe hopefully before 4.1. I don't know, fingers crossed on that though. So this is the demonstration of the clip map system, some updates there on physics. I've got a better demonstration actually of this exact same thing here. So this is the same clip map system, except instead of using a noise texture, we are moved on to actually using a real height map value. And this is one that I baked out of Gaia, if you're familiar with that. And you can actually see the clip map system working here. And one thing you'll immediately notice, one of the major reasons for the rewrite is that the actual separation between the LOD layers is much smaller than my previous iteration, which makes it even better at minimizing the pop-in in between LOD transitions. And so I'm actually going to go ahead and demo this again real quick. Here we go. So I'm going to go ahead and actually enable a debug control mode here to give me kind of a little speed boost and a bit of a jetpack capability. And you'll notice these green bars are where the transitions are. This is the visualizer turned on for the clip map system. And if you look carefully, you'll see maybe a tiny bit of pop-in, and it's really only easy to see because of the coloration changes. The only places you'll really strongly notice any transitions in LOD pop-in is going to be at the ridges. So what I'm going to do real quick is I'm going to also turn off that visualizer. It should be gone now. Cool. We'll make this a little bigger. Alright, so now when we move around, if you look really closely at some areas, like these are some trouble areas just because of the orientation of this ridge, this hard ridge, and the direction of the grids. It's actually currently opposite the direction of these triangles. You can see this edge goes this direction. So right now from top left to bottom right, and so that ridge actually runs exactly perpendicular, which makes it a trouble area. You'll notice some pop in there, but you won't typically notice it in anywhere else. So as we transition, ignoring the really far clipping plane right now, which is having some little pop-in issues right now, but that's just because it's the very extents of the camera. So ignoring that though, we'll see a little bit of transition right here, but overall you don't see hardly any transition anywhere else on the mesh, so pretty much eliminated any noticeable pop-in which is awesome. You'll see a little bit on the mountain from time to time, but nothing significant, and a far better result than what we had before, and obviously enabling a very large scale open world. So that said, we're going to pop over and talk a little bit about the water shader updates. So here we are on this kind of all together project. So we've got two clip map systems. We have one for the terrain and we have one for the water. I have brought my water shader over, and of course in the process realized that my water shader is not actually going to work really well with the clip map system, unfortunately. Due to some limitations of doing vertex-based calculations as the resolution of the mesh transitions, we end up getting some weird artifacts that make it look kind of terrible. So I've tried playing around with some stopgap solutions here and there, such as kind of implementing this noise-based radius around the player that will render some of the effects. And another big issue that it has, although it's nice and stylistic looking, we do have an issue with it looking a little too repetitive and a little too noisy over a large area like this. So as we get really large scale, it starts to look a little too repetitive and a little too noisy. So I did update a lot of things in it though. So I rewrote the wave system and the wind system so that everything is based completely off of wind direction and is scalable up and down. Even just running the transitions actually took a little bit of extra time, but so we can dynamically scale everything up and down really smoothly. Before this had some issues transitioning. It was a little, it would iterate a little glitchy in the process, but I need this to be able to scale up and down while the game is running without looking too weird. And of course we have two blended values here so we can interpolate between them. So we have the wind direction and the wind power. So we can rotate the waves around. And as you can see, it has this little bit of a glitchy effect to it, so that's what the interpolation is there for. And yeah, I just overall wasn't super thrilled with how it was looking on the clip map system. Doesn't look nearly as nice as it did in isolation. Still kind of pretty, but I definitely gonna have to go back to the drawing board a little bit on the water shader and write something that is gonna look a little better on this. So I went ahead and started another project here. There's almost nothing to it yet, but I've basically just written shoreline edge detection. And this one functions a little differently. This is actually a two-dimensional shader being performed inside of a viewport. So it's a shader on a color rect, which doesn't show anything, unfortunately, inside the 2D viewport. But it's performing all of its calculations on a two-dimensional shape and then passing that information as a height map over to the three-dimensional vertex displacement shader. And so there really isn't much going on inside the shader right now. I haven't written in any of the things that make it look really pretty, but another issue I'm fighting with right now is trying to figure out how to implement screen space reflections, or SSR, because with large islands and terrains, we at least want this kind of a silhouette to reflect off of the water, right? Part of an issue that I'm running into right now with Godot is that there's not a combined support for reflections and transparency. So once this is a transparent surface, you can no longer get screen space reflections, at least not the native screen space reflections. So I'm either going to have to write a custom screen space reflection that will support transparency, or figure something else out, but that's where I'm at on that. And I think that kind of catches us up on everything. The only other things I'm working on right now is I also started some very minor projects for procedural generation for certain things, such as trees, vegetation, that kind of thing. So I was writing a bit of code for a procedural tree generator. Still haven't fully decided whether or not I actually want to procedurally generate them or just bake a few assets out of Blender, especially for the more stylized look. That will probably end up looking better, but of course the procedural is just a kind of a cool project. And I might post some videos on that if I do go that route. So one of the other things I'm working on is implementing a texture array system. So right now, as you can see, we're simply reusing the same height map, normal map, diffuse map at each of these given tiles. Obviously, for a large-scale world, you want to be able to implement different height maps and different materials, and of course have the colliders sample those at different distances and things. So that's currently in the works. And of course, other than that, I'm going to implement splat mapping so that we can start actually applying some vegetation, textures, and additional detail normal maps, which I didn't actually touch on in this, but we do have the capability to implement those inside of the scene as well. So this one actually has a normal map, and we can scale it in and out. And you can see it makes a little bit of a difference. It over brightens a little bit right now just due to some of the settings not being quite right, but you can see that there's not a significant difference between the height map generated normals and the baked normals. However, once we incorporate some splat mapping and we have normals based on textures such as grass and rocks and things of that nature, this will make a much bigger difference on a much closer perspective. So we'll have that implemented. And of course, we can use splat mapping to also generate seed locations for things like grass and trees and other props and assets on the terrain. So all really useful stuff there. That'll be coming pretty soon, hopefully, as I get time. We'll see how the holiday schedule goes. So I know this was a much longer video than usual, and I apologize for that. I kind of rant and rambled a little bit. I have a lot of editing to do on this clip to edit out screaming and laughing toddler and some other little bits in here and there. So hopefully this was informative. I know this isn't covering as much detail as I normally do, but I just realized there's a ton of stuff to catch up on. So stay tuned, I guess, for more updates, and hopefully we see some fixes in the next iteration of Godot as well. Thanks.